So we need to prove this formula, and to do that we will begin by drawing a picture, as I have done over here. And in the picture I have drawn the real principal axis of R. So R dot n is n, and I have also drawn the invariant plane. Okay, so that's the invariant plane, okay, which is normal to the real principal axis n. Okay, now what I am going to do is I am going to put a vector here, which this vector is a, okay, and I have gone ahead and projected the vector onto n. So this is a, actually let me modify this. I won't call it a, I will call it R for reasons you will see. So this is R and the projection is R. I am going to actually call it R0, so that this becomes R0 dot n, that's the projection along n, and the projection onto the invariant plane will therefore be some vector R0 perp. Okay, that's too small, so let's rewrite it to make it more legible. R0 perp. Okay, right. So vector R in some random direction projected along the real principal axis as R0 dot nn, and in the invariant plane as R0 perp. Now for future reference, what I am going to do is that I am going to just call this direction as I, okay, so that the direction normal to n and I will be a direction j, which I will draw shortly. Now what does R do? What do we know? This tensor R, we know what it does is that it takes hold of this object and rotates it in a cone along n. That's what we have learned about the rotation tensor, and it rotates in this direction by some angle theta. So let's draw that. So what happens is that this R will come out to be some vector here. Okay, so this will be the new R. So what has happened is that we had R0 and now it's gone and become R. When it becomes R, it has moved on this cone, right? Okay, so it's okay, so that's wrong choice, I meant this. Okay, right, and the projection of R onto the invariant plane, let's draw that. Okay, so this projection will give me a vector which is R perp. Okay, and what we know is that R0 perp and R perp have the same length, and this angle will be theta, or maybe I should make it black. Okay, all right. Okay, so that's what we have, and that's projection. So let's kind of make it a dotted line here. Okay, so that's the situation. Okay, so what we have is initial vector R0 becomes R under the action of the rotation tensor capital R. So now let's write down some formulae. Okay, so what is clear is that R0 can be written as R0 dot n plus R0 perp. So you will have no problem with that. That's simply this projection along this and this. Okay, great. Now what I can also do is I can write down R0 perp as minus n cross n cross R0. Okay, so this is just a formula which you can check. You check. Okay, so I will use this for future reference. Meanwhile, I can also write down r similarly as r dot n plus r perp, right? So all I have done is that I have gone ahead and projected this r onto the n axis also. Okay, so that's the projection, and clearly r0 dot n, I mean these two things are the same, right? So there is no problem with that because they are along the n axis and they are not affected by r, by the rotation tensor r. So I can write this as r0 dot n plus r perp. Okay, so it's this creature that we need to understand a bit more. So let's do that. So I can write down r perp as I can project this vector along I and the normal to n and I, which I said earlier on I will call j, and I have not drawn till so far. Now I shall do so. So it is some vector, let's call it j. Okay, and j will be obviously equal to n cross I. Okay, that's by definition. And okay, so maybe it's getting a little messy over here, so I will kind of rewrite this over here so that it's clear. Okay, so that's it. So I, j, n is a Cartesian coordinate system. Okay, great. So I can now write down r perp as r perp, the magnitude, into I cosine theta plus j sine theta. So you will have no problem with that. And then using the fact that j is related to n cross I can write down this as I cosine theta plus sine theta n cross I. Okay, so no problem. Now I will also remember that capital R is a rotation tensor, therefore the magnitude of r perp is the same as the magnitude of r0 perp. So what I am going to do therefore is I am going to write down here r0 perp. Okay, so that's the setup. Let's make this view as seamless so we can go to the next page. Okay, great. So now I need to combine these these formulae. Okay, so let's do that. So here let's open this up. r0 along I, the magnitude these two is simply r0 perp, right? So let me write that out here. r0 perp along I is simply r0 perp. So I get r perp to be r0 perp cosine theta plus sine theta n cross r0 perp. Okay, so that's good. So I have been steadily trying to convert r and r perp in terms of r0s and r0 perps. Okay, so now what I am going to do is I am going to replace r perp here. Okay, so that's what I am going to do, and when I do that I will get r as r0 dot n plus r0 perp cosine theta plus sine theta n cross r0 perp. Okay, so I have done nothing spectacular so far. Now I am going to do things. I am going to add r0 perp and subtract r0 perp. Okay, no harm in that. I can add and subtract anything. And second thing I am going to notice is that n cross this is the same as n cross r0, because what is r0? Well, you can check this fact from here. If you take n cross r0 here, then n cross n is 0 and n cross r0 becomes equal to n cross, well, n cross this will be n cross this, because this will go to 0, right? So that's what I have done over there. Great. So then r becomes equal to, I have added and subtracted these, so these two will combine to give me r0. That's what I am going to write down, r0, right? So that is these two. Then I get cosine theta minus 1 r0 perp plus sine theta n cross r0. Almost home, just that I have r0 and r0 here, but here I have r0 perp, but thankfully I have derived a formula over there. r0 perp I can express in terms of r0. So let's copy this formula from here and put it over here and combine these two. So combine to get something fishy here. That's an r vector. Get r is equal to r0 plus 1 minus cosine theta into n cross r0 plus sine theta n cross r0. Alright, great. Now that is a vector formula. Okay, it looks like this, right? These two look the same, but there is a capital, there is a tensor here and there are cross products here. Thankfully we have learned that we know that every cross product can be expressed as the operation of an antisymmetric tensor, okay, where n is the antisymmetric tensor associated with n, and we discussed this a while ago, right? So n in any coordinate system will be 0, minus n3, n2, minus n1, 0, 0, and n3, minus n2, n1. Okay, now I can take this, use this fact, and I can write down that r is r0 plus 1 minus cosine theta n square dot r0 plus sine theta n dot r0. Okay, do you see how this becomes this? It's very simple. N cross r0 is n dot r0, and n cross this is equal to n dot this, which is equal to n square r0. Okay, so there I have a formula which looks very much like this, but still not yet done. So I can express r as identity plus sine theta n, that is this one is here, plus 1 minus cosine theta n square, this whole thing operating on r0. Okay, there. So if I have a vector r0 which under the operation of the tensor capital R becomes small r, then this is the relationship between these two. But we know that, okay, I made an error again, this is a vector. We know that R is the rotation tensor times R0. So if you were to compare this formula and this formula, right, if you compare, you will get that R is 1 plus sine theta n plus 1 minus cosine theta n square, okay, which is what I have over here, and that's the proof.